You are about to be fixed. Physics Fixed. Better than real. Where each brief episode brings insight you've never had before, no matter how much time you spend in a lab. If you know enough physics to see its gaps, you'll find many fixed in this series. It's Occam's razor in the hands of Jack the Ripper. Applying a light touch identifies an ongoing experiment capable of deciding pinholes versus photons. Phyxed employs Euclidean interval time coordinates to model the particle aspects of light completely and more simply as direct contact via pinhole or particle interaction wormhole, bypassing space and time of any span. Unavoidable distortion in conventional space-time suggests separation, though the world line of a photon actually has zero span. Phyxed asserts, no world line, no particle. But with over a century of success, the photon model is extremely well established. Einstein's Nobel-winning description of the photoelectric effect was decisive in establishing light's particle nature. He envisioned light particles carrying energy from emitting to absorbing electrons. Under certain conditions, this knocks absorbing electrons free from a metal plate. By contrast, a pinhole provides remote contact by spanning measurable external distance while having zero internal extent. One electron may thus transfer a light quantum to another by direct interval contact. Such remote collisions explain the photoelectric effect without invoking a massless particle. But is there a way to prove pinholes versus photons? Phyxed answers with a simple, definitive test. A collision of two electrons may seem mundane, but contact between an electron and an anti-electron, or positron, results in their annihilation, with signature gamma ray emissions, which are in turn contact with their detector. So if light transmission is actually direct contact via pinhole, a positron absorbing the light from an electron will result in what Einstein might have called spooky annihilation at a distance. It so happens, as the culmination of 20 years' work, the Alpha team at CERN is busy obtaining the absorption spectrum of antihydrogen, the antimatter counterpart to ordinary hydrogen. They recently published a result for the 1s to 2s transition matching normal hydrogen as expected. Trouble is, 1s to 2s absorption involves two coincident light quanta from opposite directions. As noted, the frequency of transition, driven by two photons, is consistent with that expected for hydrogen in the same environment. But annihilation is strictly quantized, 1-to-1. A positron never annihilates with a fraction each of multiple electrons. Like a rock star crowd surfing a field of hands, a positron being manipulated by an electromagnetic field involves only fractional contact from many field members, so it doesn't annihilate. However, exchange of a single light quantum is distinctly 1-to-1, and for the first time could document remote annihilation. Another problem is that thick wires surrounding the apparatus block gamma rays from the annihilation. Dr. Madsen states, detecting the gamma rays from positron annihilation is very inefficient, in particular due to the magnet windings they have to pass to get to any detector. We must await alpha results for single quantum absorption and urge alpha to place a gamma detector on the light source. In that case, remote annihilation will first produce a gamma ray from the emitting electron, followed very shortly by another from the absorbing positron in the trap. Remote annihilation isn't so spooky once you've grasped invariant interval contact. Indeed, the greater burden would be to explain why, if this is not observed. Let's follow alpha developments closely, because when it comes to remote contact via pinholes, seeing is believing. Congratulations! You've been fixed. Better than real. Be sure to subscribe so we can keep in touch. Next, Phyxed teaches aging with grace in What Time Is It? I'll see you there, if you dare. Ha ha! Don't miss Alpha CERN video links in the description below.